Hey there, Math 227, Professor Talbert here. There was one example we saw in class that we didn't quite get all the way through, or didn't get to at all, and it's this one about finding a standard matrix for a transformation. So we have a transformation that goes from R2 to R2, and the way it works is when you put a vector into this transformation, it rotates it about the origin by negative 3 pi over 4 radians, and then flips the result across the horizontal axis. And so what we're going to try to do here is find the standard matrix for t. That will be a matrix A such that t of x, running a vector through this transformation, is equal to A times x. So I'm looking for a matrix whose multiplication does the same thing that t does. It does this flipping and rotating. We've learned in class a theorem, Theorem 10, that says tells us how to find this matrix here, and it says I need to find the images of two particular vectors. Find the images under T of the columns of the 2 by 2 identity matrix, and it's 2 by 2 because the domain of and codomain of this transformation is R2. So I need to find the images of two vectors, 1, 0, and 0, 1 under this transformation. And we're going to do that by drawing. Once we find those two images, those are going to be the columns of the matrix that we want. So let's go over here to the left and draw a set of axes. And I'll just do that here. And let's find what these images are. In fact, we're going to draw two sets of axes, but here's the first one. First of all, let's find the image of 1, 0. Now 1, 0, this isn't going to be to scale on the graph paper you see, but here is the vector 1, 0 before running through the transformation. Now the image of that vector is what we get out of this transformation. So let's think about how this is going to go. First of all, I'm going to take 1, 0 and rotate it about the origin negative 3 pi over 4 radians. That would put me to right here. I'll just sort of dash in where that would go. There is the vector if I rotated it negative 3 pi over 4 radians, but then I need to flip it over the horizontal axis. And so here is the result. Here's the image of the vector 1, 0. It's right here. Because I rotate it through negative 3 pi over 4 radians. That is the same thing as 135 degrees clockwise because I'm negative, and then flip it over the horizontal axis. Now what is that vector right there? I'd like to write down its components if possible. Now, I'm going to zoom in slightly on the vector that I just drew, and let me just kind of look at the third quadrant here, or second quadrant here. Now the vector we just ended up with was this one. After moving it around, it's here. Now that's got a length of 1. The length of that is 1. But these two places on the x and y axis are not going to be 1. This is a vector, and it makes a little triangle, a little right triangle you can see here, where this angle is 45 degrees. It's pi over 4. So what coordinates does this arrowhead have its points here? Well, the coordinates there we can find using a little bit of trig. I have a 45, 45, 90 triangle, and so this point right there is at the point x equals negative 1 over radical 2, and y is plus 1 over radical 2. So that's the image of the first vector. Let me write this down. T of 1, 0 is the vector negative 1 over radical 2, 1 over radical 2. Again, we got that by visualizing the vector as it moved around according to the transformation, and then using a little bit of trigonometry or geometry to find out what the x and y coordinates of the vector are. I'm going to erase this right here since I already had it written down. And now let's go and find the image of 0, 1 under this transformation. And I'm just going to draw another set of axes down here and try to go through the same motions. And here we are. Now 0, 1 is this vector that points sort of straight up like so. Now let's see where it goes under this transformation. I'm going to rotate it this way, negative 135 degrees, negative 3 pi over 4. There's pi over 2, and I'm going to go an additional pi over 4. So here's where it stops initially, and then I'm going to flip this over the x-axis, and so the final resting place of this vector is going to be right there. And again, let me draw a little set of axes here to represent the first quadrant, just to kind of get a zoomed in view of what this vector looks like. It's sitting out here at a 45-degree angle, and it has a length of 1. So what's this coordinate and what's this coordinate? Realize that this coordinate here on the x-axis is not going to be 1, and this isn't going to be 1 either. Again, I have a 45, 45, 90 triangle, and so the vector I get here, it's going to have coordinates 1 over radical 2, comma 1 over radical 2. And so this is going to tell me that t of 0, 1 is the vector 1 over square root of 2, 1 over square root of 2. And this is all we need to get the matrix A that we're looking for. And let's just wrap it up with this. Theorem 10 now takes us the rest of the way. That's going to say that A, the matrix that I wanted, A, is going to be a 2 by 2 matrix. And the first column of that matrix is the image of 1, 0. That would be negative 1 over radical 2, 1 over radical 2. And the second column is the image of 0, 1. And that's 1 over radical 2, 1 over radical 2. So multiplication by this matrix implements the same set of movements in R2 that the original verbal description of T did previously. But it does it in a little more systematic way. If I had a vector that wasn't simple as 1, 0 or 0, 1, I wouldn't have to visualize its movement. I could just simply multiply it by this matrix here, and that would give me my result.